So make sure you study. All right. They start very basic in this review. Finding the areas, giving your z-scores. I want sketches. Make sure you give me sketches, especially on your test. I need to see your sketches. It does two things. It helps you and it helps me. Because if you got the wrong answer and I have no sketch at all, but you looked it up and it's wrong, you get absolutely no credit. But at least if I can see that you knew where you were going with this, maybe you put it in wrong. So therefore you get some credit. Any questions on the first four? Area to the left, that's exactly what we look up. Area to the right, we have to subtract it from 1. Area in between, remember you have to take your z-scores, you have to find your areas and subtract your areas, not your z-scores. A z-score of 0 is 50% of your field right there, so that's your 0.5. Okay? Area to the left and to the right, we're going to add them together. They should have written it as an or, but they left it as an and. We're going to add those together. And if you notice, they're the same z-score. This is a good example because you can see your symmetry in your graph this way. If I take the negative and I look it up, and I'm looking up the positive and I do the 1 minus, it gives me the same as this one because your curve is symmetric about your mean. So add them or multiply by 2. Good? Even on the test, I'm going to give you some basic ones like this. It kind of leads you. Usually I try to follow the order of how we did these. Give you some basic ones, give you a probability one, then give you a, an application one. So it kind of leads you into all the parts that you're looking for. All right, 17, 18, 19, and 23 we'll get to. But 17, 18, 19, they just took this and they assigned a probability. Probability is the same as your area under your curve. The same as the percent you get off your table. So remember we started writing our probability statements. It's the same as saying the area to the left, that points to the left, of z equals 1.28. It's the same way to write that. Area to the right, it follows the arrow. In between, find the z-score, area, z-score, area, subtract your areas. And I think that one is right there. Okay? Questions on any of those? Just assigning a probability statement to it. Probability, part over whole, percent, part over whole. That technology project that we did, that little problem, was a good one for you to see that. Looking up areas under your curve, doing a percent. Hopefully it kind of like gave you a little bit of what was going on, that they're tied together. 23. 23 was just saying, find me the z-score associated with that x value. So I want the probability that x is going to be less than 1900. Find me the z-score associated with this x value, and then, because it's less, find me the area to the left. We're kind of combining everything. We know how to find the area of your z-score, left or right. We know how to find a z-score formula. I'll give you that formula, but I really like you to know just that one. This one is your really basic formula. But if you need to, I'll give you that one. So your sketch is really helpful. Put your 2200 here. If you like, put your 1, 2, and 3 here. Add 625, subtract 625, all the way down. It gets you in perspective. You'll be able to see what do I think it's going to be, less than 50, greater than 50, a large number, a small number. My z-score negative, is my z-score positive? If my z-score is less than my mean, I have to have, if my x value is less than my mean, I have to have a negative z-score. My graph kind of helps me with that. So if you forget which way to subtract, and you need to know that you're in the negative, you're going to subtract the smaller minus the larger. It fits right into your formula. So when I look in between, we're finding the z-score for 2000 using your formula. We've got the z-score. We're finding the z-score for 2500. We find your areas, and then you subtract your areas. Remember, your area always has to be positive. So if you subtract the wrong way, make sure you always get the positive one. And if you want to use your calculator, I need your calculator step. Your calculator bypasses all of that. Your calculator on the in-between is probably worth doing rather than with the lower limit, the negative 999, the upper limit. If this was 2200, you can't put your upper limit at 999 because that's only 1000. You have to go 99999. Just add a bunch of nines to it. Your lower limit will never be negative 999 anyway. But your upper limit you would have to change. You know, put it in perspective. The one that's really helpful is the in-between. It does make more sense. From here to here, my mean, my standard deviation. The last one was find me the probability that this amount will be to the right of my mean, of this number, 2450. So I use my z-score. I find my area to the right. That's the 1 minus. These are your probabilities of this happening. If it looks better to you in a percent, I have a 34% chance of at randomly selecting someone or something that's greater than 2450. Area under the curve, same as your percent. Is that all kind of making sense? Tying in together? That's the most important part of this whole thing. Percents, probabilities, make sure that they kind of tie together. For this guy, you just had to find me the z-scores. Area to the left, inverse norm. Percentile, your percentiles, remember, go from 0 to 100. 0 to 100. So if I'm looking for 85% of my field, I know my z-score has to be positive. It has to be on the right-hand side of the 0. When I do my inverse norm, flip that to a decimal, you get your z-score. Remember, even when you use your calculator, round your z-scores to 2 decimals. We round ours to 2 decimals. The calculator doesn't have the same as our table, so they're a lot more exact. So that's sometimes when you use your calculator versus a problem, you see the roundings a little off. Like that's what I like to know when you use your calculator. Okay, so for 31.
We didn't have 31.
You didn't have 31. Okay, I took that one away. You're right. 35.
We had 34 though.
You had 34. Okay. What is the braking distance? This is your braking distance one, right? 31 through 36? Now, your braking distance, we did an example of this. It is better to have a shorter braking distance. So when they're looking for the top rated tires here, we actually want the bottom of your curve. When they're looking for the bottom, we actually want the top. It's just because of the way the scenario goes. So the third quartile is still going to be, what's in my third quartile? You didn't have 31, you had 34, right?
Yeah.
75% of your data. Where does 75% of my data fall? Your mean was 45.1. This is feet.
Meters.
This is meters.
It says braking distance
In meters. So meters. Meters to feet.
I believe it's 3 point something.
Feet in a meter, because a meter is almost about the same as a yardstick.
Meters a little bit over.
Yeah, because that would be horrible in feet. You'd never break a ton. You'd always crash into somebody. I think it's closer to a yardstick. So even if it's 16
meters.
Feet. Yeah. Even if it's 16 feet, that's not too bad. But still, so what you're saying is, when you look at your third quartile, I want where does 75% cut off? When you look at your top 10, guys, this is the tricky one. Your top 10, if you're looking at this review of this tire in Consumer Reports, you will obviously want a tire that brakes, or your car brakes, you're looking for your car to brake. Your car to brake in a shorter distance. You don't want to break in a longer distance. So your top 10% is down here. Your bottom 5% is here. That's the cars you wouldn't want. The ones that take the longest to break. You want the ones that take the shortest to break. This is just reverse of what we normally do because of the way the problem is worded. Any questions on doing these? All right. Test is Monday or next day we meet.